Thanks, Yvonne, for the introduction. Yeah, so as introduced, I'll be talking a little bit about the history of QKD, focusing more on the theoretical side of the history, all the way from the birth of QKD, from the BB84 protocol, to my own research here at CQT with Marcos Mamesho. In particular, my own research with the Magic Square game in a protocol that I've named for this talk, CT23, C for Cervero, T for Tom Michael, hoping that at the end of this talk, maybe the name will catch on and people will begin using it. But yeah, so to get started, let us describe what QKD is. Your average QKD protocol looks something like this. Okay? It's usually a two-party multi-round communication protocol between two parties, Alice and Bob. The way this will proceed is that they will receive some quantum states, and then they will perform a series of local operations and public communication. Okay? So local operation, for example, you can think of as Alice and Bob independently selecting some measurement inputs, measuring the quantum states that they receive, obtaining some outcomes, and then exchanging some public information regarding the measurement inputs and outputs in order to perform some classical operations like error correction, for example. At the end of this protocol, Alice will output a key, and Bob will output another key. The hope, obviously, of a QKD protocol is that the keys are the same. Right? Otherwise, it's not much of a good protocol. And also the key is secure. Right? Secure against an adversary or an eavesdropper that might be trying to gain information about the key. Usually, this is the difficulty in QKD, right? Improving the security of QKD protocols. But there's actually a third person, namely Eve, the eavesdropper, that is attempting to get information of the key. And your task as a QKD developer is to prove the security of the key against the eavesdropper's information. Okay, so that's all you need to know for QKD. If this is all you get from this talk, I'm more or less happy with it. Okay, so now let's begin with the history. I've prepared a nice chronology from the 1984 to last year, with several stops that we will make along the way, introducing new problems and new developments to solve those problems that have arisen across the history of QKD. So we can begin with the birth of QKD, which is commonly attributed to the BB84 protocol after Brassard and Bennett, who introduced the protocol first, right? And the way this protocol would work, roughly speaking, is that Alice and Bob will select a random basis, right? Either the computational or the Hadamard basis, which I remind is an equal superposition of 0 and 1 with the plus and the minus. Yeah. So Alice will pick these two bases, and then once she's picked the basis, she will pick one of the two states of that respective basis to send. Yeah. Then she will send that state that she's picked to Bob, and Bob, what he will do is pick a random measurement basis, again, either the computational or the Hadamard, and he will measure the state that he has received from Alice in one of these two bases. Now, the key idea in the BB84 protocol is that if Alice chooses the computational basis, therefore sending either 0 and 1, and then Bob chooses the same basis to measure, then he will always find the state that Alice has sent with probability 1. Similarly, if Alice sends the Hadamard basis state and Bob chooses the Hadamard basis to measure with, he will always, with probability 1, obtain the correct state that Alice intended to send. Conversely, if Alice sends a computational and Bob chooses the Hadamard, or Alice chooses the Hadamard and Bob chooses the computational, then he will get an outcome that is only equal to the one Alice intended with 50% probability. Okay. The security is therefore guaranteed by the fact that an eavesdropper attempting to measure the state that Alice sends to Bob will provide some alteration that then can be identified by Alice and Bob when they later communicate their choice of basis. Right? I will formalize this a little bit later. More or less at the same time, our previous director, Arthur Eckert, introduced independently another quantum key distribution protocol, which I will not explain here because it's a little bit more complicated. I will instead focus on BBM92 protocol after, again, Brassard, Bennett, and Mermin, which came 1 year after the Eckert 91 protocol. It's a little bit simpler to explain. And it's more or less the same, follows more or less the same as the BB84. In this case, Alice and Bob have a source that produces perfectly entangled states, the 0, 0, plus 1, 1, which we note that is equal to the plus, 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 minus, minus state. And then we'll do the same thing. They will each choose a random measurement basis and then measure the state. Once again, if they both choose the same basis, then because of the properties of the maximally entangled state, they're guaranteed to obtain the same outcome. If they both choose the computational or if they both choose Hadamard. Conversely, if they choose opposite bases, then the results will not be correlated perfectly. They will only get the same result with 50% probability. So it's more or less an entangled version of the previous BB84 protocol. The ERC91 protocol is a little bit more complicated because it introduces an extra measurement basis that they can use to test CSSH inequality, but let's not concern ourselves with that for now. Okay, so that's it. That's the introduction of the birth of QKD, right? Roughly speaking. However, there's some problems with what we have introduced so far, right? And in particular, because QKDs are cryptographic protocols, right? As such, you need to introduce some rigorous security definitions, notions that you can quantify against a certain class of adversaries, right? And this is what the remaining of the history of QKD is about, introducing these security definitions and ways of proving these security definitions. Right. In particular, we care about how do you deal with the eavesdropper. In the previous two examples, the BB84 and the BBM92 that I introduced, there was no talk of the eavesdropper, just an honest implementation of the protocol between Alice and Bob. In particular, we also need to consider what if the quantum channels or the sources that the Alice and Bob use are noisy. Right? Before, we said that Alice sends either a computational basis or a Hadamard basis state, or that the source distributes perfectly entangled states. Well, there might be some noise involved, right? The channel that Alice uses to send Bob that qubit might be noisy, and then the state that Bob receives is not quite what the one Alice intended. Same idea for the source. Okay. That means we need to introduce some sort of error correction, right? Or alternatively some post-processing to amplify the secrecy of the key. Okay. How do we define security is a different problem. And in particular, how many bits of key per measurement round of the key rates do we obtain in a certain protocol? So basically, we need a formalism in QKD. Right. So around the BBM92 protocol, in order to introduce this security notions, it's useful to have like a round, what we mean by a round of these these QKD protocols. We proceed as follows, right? Alice would select a measurement input, again corresponding to a measurement in the computational basis or a Hadamard basis. Right? If x is equal to 0, she measures the state that row A, B, E, the eavesdropper prepares and sends the A bit to Alice, the B bit to Bob, and the E bit to she keeps to herself. So if x is equal to 0, Alice will measure A in the computational. X is equal to 1, she will measure A in the Hadamard, and same thing for Bob on his own half of the tripartite state. They will obtain some outputs, A for Alice and B for Bob. In this case, we're assuming everything is bits, right? So they have a qubit and they produce a 2-outcome measurement on this qubit to receive a single output. Okay. So after n rounds of the BBM92 protocol, Alice and Bob will each have the n measurement inputs that they have selected, x1 to xn and y1 to yn. And they will have their corresponding measurement outputs, a1 to an and b1 to bn, not a1 to an again. Okay. At the end of the capital N rounds, they will announce all the measurement inputs and then only keep the rounds in which the measurement inputs of both parties are equal. Because again, remember that if they measure in opposite bases, their outcomes are not going to be correlated. They're only going to be the same 50% of the time, right? So then they, out of the N, they on average will keep only half of the rounds in which they both measure in the same basis, okay? Right, so let's say they keep little n. Now, because of this noise that I mentioned about before, you need to error correct, because even though the measurements are supposed to be perfectly correlated, there might be some noise in the system that might not ensure that the bits outcome in the measurements for Alice and Bob are equal every round. So then to error correct, you unfortunately need to leak some information. Okay? How do you deal with this leakage? How much of the leakage do you need? And in particular, the most important part is you need to bound the amount of information that the eavesdropper has about the raw key being the n, little n bits that Alice has. Okay. So to quantify these two concepts, right? This how much information do we leak? How much information does Eve have? What we use is the concept of entropy. Okay. So in particular, we're going to be concerning ourselves for now with the Shannon entropy, which for a random variable x with some probabilities px is equal to the negative sum of px log px. As a little intuitive explanation for the entropy does, the higher the entropy, the more uniformly random your random variable is. So for example, if you're flipping a coin, 50-50% of heads and 50-50 of tails, the entropy is going to be equal to 1. Whereas if you have a super biased coin where heads happens with probability 1, tails with probability 0, then the entropy will be 0 because 1 log 1 is 0 and 0 log 0 is defined to be 0. Okay, so basically every time you see an H to be high. If the entropy is high, good. Because high entropy means more randomness. More randomness means it's hard to predict. If it's hard to predict, that means the eavesdropper has little information about it. Okay. Similar to the Shannon entropy, we can define an equivalent quantity for quantum states, namely the von Neumann entropy. For a given quantum state on, say, a subsystem, rho A, the von Neumann entropy is going to be given by the negative trace of rho times the logarithm of rho. Okay. In particular, you can think of the von Neumann entropy as the Shannon entropy of the eigenvalues of rho, but that's not so important now. Lastly, we care about the conditional entropy. This one's important because this is when we actually introduce the eavesdropper. What we care about in quantum key distribution protocols is finding the conditional entropy of A given each part of the information. Right. So this is more or less, you can think of it more or less as the same as this, except now you have a conditional probability distribution of A given E, and you want E to have little information about A, even if they share a conditional probability distribution. Okay. So once again, for a quantum key distribution protocol, we want this entropy to be high, because that means that the A part of the Alice is part of the key, even if E has some quantum or classical side information. If this quantity is high, then the randomness of Alice's key is high, and in particular, more or less secret to E. Because high entropy is randomness, which means hard to predict. Okay. Right. So from here, we have more or less the first development on how we define security or key rates for one of these QKD protocols. So in 2005, Igor Devetak and Devetak-Winter published a paper in which they calculated the asymptotic rate of a of a quantum key distribution protocol. This rate has come to be known as the Devetak-Winter rate, a very useful metric. You see it in every paper of QKD since 2005. And it tells you that if you produce a rho key of length L, okay, and you divide by the number of rounds, so this will give you the amount of key, and you take the number of rounds to infinity, that asymptotic key rate is going to be the entropy of A given E minus the entropy of A. And what does this mean? The entropy of A given E, as I was saying before, as I was arguing before, is essentially the amount of information that Alice has that is secret from Eve. Right? It quantifies the amount of randomness of Alice that is independent from Eve. And from an operational point of view, practical point of view, you may think of it as the number of secret bits that Alice has, and also Bob, that Eve does not have any knowledge about. Right? So think again the scenario of flipping a coin. If Alice flips a coin, and condition on Eve, this entropy quantity is 1, that means her outcomes are completely random and must therefore be independent. Okay? So again, we want this quantity to be high. The higher this quantity, the more randomness Alice has that is independent of Eve. Okay? And the second quantity, the entropy of A given B, essentially gives you knowledge about how much information. It basically tells you the disparity between the secret keys of Alice and Bob. This disparity is the amount of information that they need to correct. Because I remember that a QKD protocol, at the end, the key of Alice and the key of Bob should equal. Right? Which means they need to do error correction. For error correction, they need to transfer some information to each other. The amount of information that they need to transfer to correct the disparities is precisely given by this quantity. Okay? So basically, the asymptotic rate tells you that you have a number of bits equal to the entropy of Alice given by Eve, the number of bits that Alice has that Eve does not have any information to, minus the number of bits that you need to error correct. More or less, there will be some number between 0 and 1. Yeah, also closer to 1 than 0. Okay, and that's the Devetak-Winter rate. So that's the next milestone in our chronology. This happened in, it was put in the archive 2003, published 2005. So next in our timeline is chronologically speaking 2005, but we're going to skip to 2006 and then come back to 2000, just for the fun. So problems with what we have so far. Can we trust the measurement devices? Because in a QKD protocol, what happens is that Alice and Bob will have some quantum device that they input their measurement inputs to, and that read out the measurement output of the whatever quantum state that they had inside. Similarly, that quantum device is supposed to receive some sort of particle, either sent to by the other party or by the source in the middle. How do we know that we can trust that source? How do we know that it's actually producing the state that we would like it to produce? Similarly, how do we know that the measurement itself is producing the measurements that we expect it to measure? Right. So remember, again, in the BB82 protocol, the source was a maximally entangled state, and then devices were measuring in the computational or Hadamard basis. Can we remove these assumptions? Does it work if we send any state and then any measurement? Quite remarkably, as the consequence of the properties of quantum mechanics, you can. You can actually build a QKD protocol without trusting absolutely anything. Well, you have to assume that the eavesdropper is a quantum mechanical person. They don't satisfy any super quantum mechanical theories, but I feel like that's a reasonable assumption to make. So in particular, this gave birth to the rise of what's known as device-independent quantum key distribution. And it's based, the primitive of device-independent quantum key distribution lies in some protocols known as non-local games. Okay, so an example of a very famous non-local game is the CT23 game, okay, which would proceed as follows, right? Or in general, non-local games are multi-partite games played between a referee, yeah, and then however many parties that are participating in the game. In this case, only 2 parties, again, Alice and Bob. In particular, the CT23 game would proceed as follows. The referee would select a bit at random, 0 or 1, and send it to Alice, and another bit, 0 or 1, and send it to Bob. Based on that bit, Alice will produce another bit and send it back to the referee, and Bob will produce another bit B and send it to the referee. The referee will then decide whether that combination of inputs outputs is a win of the game or a loss of the game. For the CT23 game, in particular, Alice and Bob win if the product of the measurement inputs is equal to the direct sum of the measurement outputs. Okay. Now, in this kind of non-local games, we are interested in what is the probability. Again, the probability, remember that Alice and Bob receive these bits at random. Okay. We're concerned with the probability that they win if they are allowed to prepare a strategy before the game begins. That is, Alice and Bob, before they receive respectively X and Y, they're allowed to convene and prepare a strategy that allows them to win, right? What is the probability that given that strategy, they win? In particular, if they prepare a classical strategy or a quantum strategy. Okay? A classical strategy, you can think of it as a deterministic strategy. The only probability is over the choice of X and Y. A quantum strategy would also be over the randomness of quantum mechanics. So for the CT23 game, this classical winning probability and quantum winning probability are well understood. A classical strategy turns out that the optimal quantum strategy is for Alice and Bob to completely ignore all inputs. Doesn't matter the X and the Y that they get, they will always output 0. Right? Because in this case, you can check that if they always output 0, A plus B is always going to be 0. And X times Y is going to be 0 3 out of 4 times. So basically they win unless they lie, unless Alice was asked 1 and Bob was asked 1. Because every other time they always win. Okay? So winning classical probability is 3 over 4. Quantumly, you can actually do a lot better, well, a little bit better. So the strategy, once again, involves sharing a maximally entangled state, 0, 0 plus 1, 1. And then based on the measurement inputs that they decide, they will perform an appropriate measurement. So if Alice receives an input of 0, she will measure her half of the entangled state in the computational basis. And if she receives the input 1, she will measure her half in the Hadamard basis. Similarly, Bob has 2 different measurement bases, which are basically rotations of 0, 0 and 1, 1 by like 45 degrees, too long to be putting in here. It involves some cosine and sine of pi over 8, but some measurement basis. You can show that with this measurement basis and that state, the probability that they win with a quantum strategy is 2 plus the square root of 2 divided by 4, which is roughly 0.85, which is about 10% better, classically. And what's most striking about the quantum strategy, and this in particular with respect to the game, is that there's something known as the notion of self-testing. If you achieve in a version of the CT23 game, if you achieve a winning probability of 85%, then you can guarantee that even if you do not know the states and the measurements that you were playing with, you can guarantee that if you achieve this probability, then you must have been playing with a maximally entangled pair and these measurements, or some transformation and unitary transformation of these states. But that's the important part. That this winning probability self-tests the maximally entangled states and the measurements. So we can more or less use this idea for making a QKD protocol. And this is in fact what people in 2006 did. In particular, credited to Stefano Pironio, alongside Antonio Thin and our own Valerio Scarani and a couple other people in the paper. And they came up with a device-independent quantum key distribution protocol that leverages this CSSH game. Again, using this notion of self-testing, right? You force the source, the unknown and untrusted source, and the unknown and untrusted measurement devices to perform the optimal measurements you wanted to perform by ensuring that your winning probability is close to this 0.85. Right? So the way they would work, the protocol, is that Alice chooses two measurement inputs, 0 and 1, which again corresponds to would correspond in the ideal case to the CSSH measurements, either Hadamard or computational basis. And same for Bob. Bob has input 0 and 1, which corresponds to the CSSH measurements, and then an additional measurement input corresponding to the measurement basis, computational basis. The idea would be that if Alice and Bob both select inputs in 0 and 1, they're essentially playing the CSSH game with the same measurement basis. If those rounds give you a winning probability of close to 0.85, then you can guarantee that you're playing with an entangled state, which means that in the rounds measures with 0 and 1, and Alice also measures with 0 and 1, because you were playing with the 0, 0 plus 1, 1 state, the outcome of this measurement and that measurement must be perfectly correlated, which is good enough for a key, because then you guarantee to obtain the same measurement outcome. So more formally, you have two types of rounds in a QKD protocol based on the CSSH game. You have a testing round, in which case Alice and Bob are playing the CSSH game from before. And you have key generation rounds, in which Alice inputs a 0, which remember is for the computational basis, and Bob also inputs a 2, which is also the computational basis. If in testing rounds, the probability that you test of winning the CSSH game is close to the maximal one, because of self-testing, you guarantee that you're playing with a maximally entangled state, which means that these measurements are supposed to be maximally correlated. You obtain the same outcome with probability close to 1. With this information, knowing nothing about the states, what these authors were able to prove is that if your winning probability is close to maximal, then you can get a bound on the entropy of Alice given the Eve's information, which remember is the quantity of merit that we want for a QKD protocol, which is equal to something like this, where h, the little h is the entropy of a binary variable, either x or p or 1 minus p. Okay, something like this. You don't have to know what that looks like. But the point is that even if you don't know anything about the measurement devices or the source, you can still get a bound on the entropy. So that's more or less the idea behind behind the origin of device-independent quantum key distribution. And then we go back in time, because we still have some problems, right? As I said before, the entropy, the quantity of the entropy of A given E is only relevant as a figure of merit because of this Devetak-Winter rate, which, as we said before, is a guarantee the number of rounds when the number of rounds go to infinity. These protocols that have an infinite number of rounds obviously take a long time. So they're not necessarily practical or practical implementations or real-world implementations. So we care about protocols in which there are only a finite number of rounds. And also defining a good security notion for these finitely round protocols. In particular, the issue is that the von Neumann entropy that we dealt with before is it's an average case measure of randomness. Because again, remember, it's the sum, it's a weighted average of the log of the negative log of the probability. Right? And then you average it over all the probabilities. This is only an average case measure of randomness, and maybe it's not stringent enough for finite round protocols. Okay. So this is precisely what Renato Renner, he's doing his PhD, was trying to concern himself with. And in particular, the intuitive definition of security for finite round protocols that he came up with is as follows, right? So a finite random quantum key distribution protocol at the end will output some key K of length L. Right. So therefore, the classical quantum state produced at the end of the protocol, again, is going to be some state on K, the key, and E, the side information, quantum or classical, that the eavesdropper has. In particular, it's going to be some key, just given by the outer product of K, which is a bit string from the two L bits. Each of the 2 to the L combinations happens with some probability pk. And then for each of these possible key states, the eavesdropper will have a correlated state. So it'll have a state E that depends, that is conditioned on that particular string. In contrast, an ideal quantum key distribution protocol, again, remember intuitively, a quantum key distribution protocol is a protocol for distributing keys. Okay? Keys that will be subsequently used for other cryptographic applications, quantum or classic. The point of a cryptographic application is that the keys, usually these protocols are only secure if the keys are perfectly uniformly. Okay. So ideally, a quantum key distribution protocol should produce a perfectly uniformly random key that is secret from the eavesdropper. So in particular, a QKD protocol's ideal state should produce a state KE on registers KE, where the register K is a completely uniform state containing the key, a uniform sum over all possible L bits, L length bits, and then a completely uncorrelated rho E. This rho E does not depend on K, whereas this rho E does depend on K, and then pk is some probability, and here we have a perfectly uniform. Okay. So how do you quantify the security of a protocol? Well, you compare the ideal state produced by an ideal QKD protocol and the actual state produced by an actual QKD protocol. How do you compare them? With some distance measure. It's common to use the trace distance, which I'm not going to define, but it's basically the distance between some distance measure between the two states. Right? So we basically say that a QKD protocol is epsilon sound if the distance between the ideal state and the actual state is smaller than this epsilon sound. Okay. But now we have a problem. How do you compute this distance? Especially in the device-independent case, where we have no idea what this looks like, because we don't know what the original quantum state that Alice and Bob received was, and we do not know what the measurement devices were. How do you compute the state, and how do you compute the trace distance? So this is what Renato Renner does. Before that, I need to introduce some other quantities. In particular, the min entropy. Okay, so more or less related to the Shannon and von Neumann entropies from before. It's just a little bit of a harsher to satisfy this. So for a random variable x with probabilities px, the min entropy is the negative log of the maximum px. Okay, so comparing it to the Shannon entropy from before, the Shannon entropy was a weighted average over the probabilities px, whereas this one takes the worst, or rather the maximum probability, and takes the negative log. So this min entropy is always going to be smaller than the von Neumann entropy. Right? And remember that what I said before, the higher the entropy, the better for our scenarios. We want high entropy, more randomness. The min entropy is going to be smaller than the Neumann entropy or the Shannon entropy. So we're going to certify less entropy, but it's going to be a more secure source of randomness because it's a harsher requirement to satisfy, more or less. Yeah. We can define a quantum counterpart to the min entropy. And in particular, we're going to be concerned with the min entropy for classical quantum states. So as with before, a classical quantum states is some classical state x happening with some probability px, and then some state rho, quantum state rho, that depends on this x. Okay. For the conditional min entropy on x given e, not a, is the negative log of the probability of guessing x given that you know e. What is the guessing probability? Well, is you take the state that you have on the E side, you choose the best P of M given X, and then you average over all the X's. Roughly speaking, you can think of it as the same thing. You take, given that you know E, for each conditional probability given E, you take the best or the highest probability of X for each X given E, and then you average over all the X's. You can think of it as the same thing, more or less. Okay, so now, how do we prove soundness as given by that trace distance from before. So in a finite round protocol, you can have n measurement rounds, and you're going to have some rocky S, which corresponds to the, say, the measurement outcomes, n rounds, A1 to AN. Yeah, so this is mainly the work of Renato Renner during his PhD. What he said was, if you put this rocky S through a randomness structure, I'm not going to define what that is, it's some classical operation that extracts randomness. The outputs of the randomness structure, which is going to be your final key, and suppose that it is of length L, is going to satisfy the following. The distance between your actual quantum key distribution state output and the ideal state, I think this is the one from before, with tau k being the maximally uniform, is going to be upper bounded by some quantity that depends on the min entropy of the raw key, not the final key, but the raw key that you put through the randomness structure. Addition on that information of the E. Ignore that little epsilon. It means that it's an even more stringent requirement than the min entropy. And in information theory, basically, this is the worst case measure of randomness that you can certify, right? Which makes sense, right? If you want something to be secure, you take the worst case guarantee. You assume the eavesdropper is amazingly powerful, and then you take the most stringent security definition, and that's what you certify. Okay. I put a little picture of Marco Tonomichel on the side because I think this specific version of the theorem is one of his results that came a little bit later. Renato's was slightly different, but it's more or less the same spirit. You need to bound this min entropy base. So essentially, to prove soundness of a quantum key distribution protocol, what we care about is providing a lower bound to the min entropy of the raw key, given the eavesdropper side information. So we've turned the requirement of upper bounding the trace to lower bounding the entropy, which more or less puts us back into familiar territory. A quantum key distribution protocol, we want to certify that the output key produced through a random process is random enough. Lower bounding this min entropy tells you that under some definition of entropy, it's random enough, the key that you produce. Okay, that's what happened in 2005. So now we can move on. What's the problem? We can't compute that in practice, right? So if Marco was here, he would be giving me the stink eye a little bit. The min entropy is a well-defined quantity that corresponds to a well-defined optimization program, known as a semi-definite program. But this doesn't really help when you have when you need to calculate it explicitly for a quantum key distribution protocol. Okay. It's very hard, right? Especially again in the device-independent case where you do not know anything about the protocol, just the measurement inputs and the outputs. Okay. So then, can we turn it into an easier problem? Can we lower bound it? Well, it took some time until people found out how to lower bound this quantity. It was up until like 2008 when a certain Swiss man began his PhD in ETH. Okay. So basically, for his first paper of his PhD, he dropped the quantum version of the asymptotic equipartition property, which basically what tells you is that if the raw key is produced in a round per round basis, where all the rounds are identical and independently distributed, then the smooth min entropy of the bits A1 to AN, given the identical eavesdropper side information E1 to EN, is lower bounded by n times the von Neumann entropy per round of the protocol. Which again brings us back to the Devetak-Winter rate, which what it tells us, the figure of merit is the per round von Neumann entropy. In particular, if you divide both sides by n to find the key rate and then take n to infinity, this gets killed, right? Because that goes to 0, root n over n as n goes to infinity. And then we only remain with this entropy. So again, we retrieve the Devetak-Winter rate in some sense. So that's precisely the quantum version of the asymptotic equipartition property. And this was the first time that we had a way to prove to lower bound the smooth min entropy for security of key distribution protocols. And that's what happened in 2008. So what are the problems with this? What is the adversaries more general? The asymptotic equipartition property only works if every round is identical and independently distributed. Why would we assume that the eavesdropper does the same thing in every round? It's much more natural to assume that the eavesdropper can basically store every round and then perform a global post-processing map once he knows all the information about, say, error correction that they had to make, that Alice and Bob needed to make public, every other information or piece of communication that they exchange, every knowledge that he's managed to store, he can perform a big global POVM on all the rounds and all the information that he has over all the rounds. Surely this is it's a more powerful adversary, so the security guarantees against this powerful adversary will be a lot stronger, right? So in particular, yeah, that's what an adversary having quantum memory and a coherent measurement strategy means, right? That they're able to act on the entire catalog of the QKD distribution protocol. So it took from 2008 up until 2016/18 to be able to get a lower bound on the smooth mean entropy in the non-identically and independently distributed round. And these are basically what are known as the EAT theorems, the entropy accumulation theorems. Yeah. The first one was by Frederick Dupuy, Omar Fauci, and Renata Renner. And then a few years later, in 2022, there was another paper also including the same three authors and Tony Metger for the generalized entropy accumulation theorem. So what do these theorems tell you? It tells you that if the eavesdropper behaves in a general but natural way, namely that the eavesdropper is essentially no signaling, which basically tells you that the measurement devices or the measurement devices that the honest parties use their outcomes do not depend on the inputs of future rounds, which makes sense. Everything should be within the same light cone. If the eavesdropper does not violate this light cone, then the entropy of the Rocky condition on a single global adversary is more or less lower bounded by the sum of the entropies in every round. Which is in spirit more or less the same as the asymptotic equipartition property that we had before, right? That again, the figure of merit is calculating the entropy, the von Neumann entropy of every round. Once again, you know that if you divide both sides by n, and then you take n to infinity, this root n term gets scaled, and this stays as is because you have a sum over n. Okay. So once again, in the asymptotic case, we retrieve Devetak-Winter von Neumann probability. Yeah, and that's more or less the stage of. There's a few things that I skipped in the. Most people were not sitting idle from 2008 to 2018, but I only have 1 hour, so that's basically up until 2022 with the generalized entropy accumulation theorem. I should say there are more entropy accumulation theorems now, but I'm not going to talk about them. So now, in the last 20-ish minutes, I'll talk about what I've been up to, what CQT pays me for. Yeah. So the objective of my own research has been to apply these techniques to see if we can build a device-independent quantum key distribution protocol from any monogamy of entanglement game. Now, what is a monogamy of entanglement game? Well, it's kind of related to the non-local games we were talking about before. To exemplify it, I will deal with I will introduce you guys to what was the original motivation to my first research project at CQT, which was the Magic Square game. Another type of non-local game, like the CHSH. In this case, the referee is going to distribute to Alice either 0, 1, or 2, and Bob, again, either 0, 1, or 2, also uniformly selected, okay? And Alice is going to respond to her query with 3 bits of even parity. That means the 3 bits need to have an even number of ones. So there can be only one of these 4 possible strings. And Bob, to his input of 0, 1, or 2, he also needs to reply with 3 bits, but such that his 3 bits have an odd parity, that is an odd number of ones. Okay. And then they win if the y bit of Alice is equal to the x bit of Bob. Okay. Seems pretty abstract, but basically what this game is telling you is that Alice is going to be given, if you think of a 3x3 grid, okay, imagine Alice is given one of the 3 rows of a 3x3 grid, either row 0, row 1, or row 2. And Bob is given one of the 3 columns, either 0, 1, or 2. So in this case, Alice has been given row 1, and Bob has been given row 0. They're asked to fill the 3 squares in the respective row and column, fulfilling their parity conditions, right? Alice needs to have an even number of ones, and Bob an odd number of ones, and they win if the overlap between the row and the column is the same. Okay, so in this case, Alice outputs 0, 1, 1, and Bob outputs 0, 0, 1. And because the overlap 0 is the same, they win the game. Okay. Once again, we are concerned with the probability that they win if they're allowed to prepare a classical strategy or a quantum strategy. So what's the optimal quantum strategy? Well, Alice and Bob can completely agree on a filled grid before the game begins. And then once the game begins, they basically, Alice will receive a row, Bob will receive a column. They look at their grid that they have from before, and they basically read off it. Okay. The problem is that with the parity conditions, it's impossible to perfectly fill one of those grids. So I filled one here for you. Alice could choose the first column to be filled with zeros. That's fine, even number of ones. The second row also with zeros. Fine, even number of ones. And then to satisfy Bob's parity conditions with an odd number of ones, the first column needs to be filled with a 1. The second column also needs to be filled with a 1 on the last square. And now we come to a problem on the last square. For it to satisfy Alice's row conditions, this would need to be a 0. But for it to satisfy Bob's condition, it would need to be a 1. So they can only ever, with every combination, it holds that they can only ever fill 8 out of 9 squares. Okay? So basically, because they receive the row and the column at random, they win every time unless the overlap of the column and the row coincides with the one spot that they could not fill. Because they receive a row and a column and at random, then they fail 1 out of 9 times and they win 8 out of 9 times. So the classical winning probability is 8 out of 9. Approximately 0.88. Okay. Now, quantumly, there exists some strategy. What they can do is share 2 maximally entangled states. So Alice gets 1/2 of the first and 1/2 of the second, and Bob gets the second half of the first and the second half of the second. And then they perform, according to the rows and the columns, they share this grid of observables. And then they measure according to those observables, and they read out the corresponding measurement outcomes. You'll notice that if you multiply the observables in each row, they're always going to give the plus identity, right? This identity times set gives identity. Set times I times set gives the identity. So then the parity of every row is going to be 1. And similarly, if you multiply the columns, you're going to get the minus identity, right? X times minus X is minus identity, and set times set is the identity. So every column is going to give you to the minus identity. In particular, this means that the outcomes will satisfy the parity conditions that Alice and Bob have from before for the 3 bits that I introduced before. And in fact, you can show that using this 2 pairs of maximally entangled states and this measurement strategy, they can always win with probability 1, no matter what the row and column inputs are. Okay. So before I mention this notion of monogamy of entanglement, monogamy of entanglement games refer to versions of this kind of non-local games to which you add an extra player and then see how the winning probabilities change. So in particular, this is what we do. We come up with a tripartite magic square game, which is the same. We have some Alice that receives either 0, 1, or 2 and outputs as before. Some Bob that receives 0, 1, or 2 and outputs as before. And now we add an extra player, Charlie, okay, which will receive both the inputs of Alice X and Y of Bob, and will be tasked with outputting a single bit, C. Okay. Now the winning condition is that the 3 of them, which again play together, Alice, Bob, and Charlie win. If Alice and Bob win, the 2-player version, the overlap is the same. And in addition, Charlie guesses that overlap. Okay. So now if you think of the grid, Alice and Bob need to match on the point where the grid crosses, and moreover, Charlie needs to guess what that overlap was correctly. Okay. So again, the same classic strategy from before works. Alice, Bob, and Charlie can prepare a grid that they can only fill 8 out of 9 squares, and then they basically read off that grid whenever they get their inputs. They win every time. They don't get the square corresponding to the one they couldn't fill in. Okay. How about quantumly? Well, the idea is that because the quantum strategy that allows Alice and Bob to win with probability 1 requires Alice and Bob to share maximally entangled states, the idea is if you add a 3rd player, the maximally entangled state for 3 players, the GH set state, for example, the correlations afforded by the GH set states alone are not enough to actually perform any better than the classical strategy. Right? So you remember maybe one of the first slides on the BB92 protocol, I said that 0, 0 plus 1, 1, the maximum entangled state, is equal to plus, 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 minus, minus. And that's why the two-party case works, because 0, 0 plus 1, 1 is equal to plus, 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 minus, minus. This does not work if you have more than two parties. The GH set state on three parties, 0, 0, 0 plus 1, 1, 1, does not equal to plus, 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 minus, minus, minus. Okay? And that's where all the correlations break down. Exactly why we have this monogamy of entanglement. Right, the correlations afforded by a two-party maximum entangled state are so much stronger than the correlations afforded to the three-party case. So that's why we began this project thinking, okay, we want to show that analytically, that quantumly, the winning probability of three players is actually the same as the classical maximal winning probability, namely 8/9. But this was a little bit hard, and we never managed to show this analytically. We turn to numerics. There's this sequence of optimization programs known as the NPA hierarchy that give you an approximation to these hard optimization problems. And upon some months of optimizing these programs, we managed to get an upper bound on the quantum winning probability of 8.000057, which is not bad, but it's not, exactly the 8/9 we wanted. Okay. As a theorist, I'm still a little bit upset about this. I would like to have the 8/9, but I still have some time left of my PhD that maybe I can devote to finding an analytical solution to this. The point is that for quantum key distribution, this is good enough, right? Essentially, we have that the quantum winning probability is the same as the classical winning probability. Now the problem is, how do you turn this to quantum key distribution protocol? Well, intuitively, if we go back to the bipartite case, you can think of this as a quantum key distribution protocol in the following way. Alice will select an input, produce 3 bits. Bob will select an input, produce 3 bits. And then they will communicate their respective inputs. Okay. And then their key bit per round will be precisely AY for Alice and BX for Bob. If they were playing two players only, then because of the quantum strategy winning the probability 1, they can guarantee that AY is always going to be equal to BX. So then it's a suitable candidate for a QKD protocol, right? You have a process wherein every round that you play this process, you always generate the same bit. Okay, good enough for a quantum key distribution protocol. But then comes the problem of the eavesdropper. What if there's a third player? The point is that because we've shown that if there is a third player, the winning probability of the 3 players is equal to the classical probability of winning, which is 8/9. The difference between the probability of 1, if they were playing alone, to the probability of 8/9 allows them to detect this eavesdropper, intuitively speaking, right? Say they play 100 rounds. If they were playing alone, then they expect to win 100 of those rounds. Right? But if then they compare the 100 rounds and see that they've only won 8 out of 9 of those rounds, so like 88% of those rounds, then they can be like, wait, hold on. There's probably somebody listening in, because we should have been winning all of them, but now we're getting exactly the probability of winning as if somebody else was playing with us. And more or less, that's the proof. The protocol would go as follows. Alice will select some measurement inputs, 0, 1, or 2, same with Bob. Produce the 3 bits. After n rounds, they will announce the measurement inputs. Select the key bits as before. So this now denotes A1 of Y1 denotes the Y1 bit of the output A1. But yeah, the Rocky bit from before. And same with Bob's Rocky. Because of the generalized entropy accumulation theorems from before, we can restrict our view to the single round versions of these games, which is precisely the one we have these guessing probabilities for. Okay. So now the ultimate thing that we have to calculate is the entropy of Alice's key bit generated in each round, namely the overlap bit, conditioned on any third player in this game information. Okay. I should clarify that the reason why they're called monogamy of entanglement games, the monogamy of entanglement property is the fact that the game winning probability from 2 players to 3 players decreases by virtue of the 2-player strategy requiring maximally entangled states. Because of monogamy of entanglement, there's this decreasing probability, hence why they're called monogamy of entanglement games. They only work because entanglement is monogamous. Okay, but yes, we need to concern ourselves with the, again, von Neumann entropy of each round. So, similar intuition as with the CSH. After playing some time, Alice and Bob will estimate the winning probability of their magic square game, which should be somewhere between 8/9 and 1, 1 being the best case scenario and 8/9 being the 3-player scenario. And we recall that this 3-player winning probability is more or less 8/9. Okay. So that's a quick proof of the von Neumann entropy bound. So if you let GE be the event that Eve guesses correctly, and WAB be the event that Alice and Bob win, okay? So in fact, probability of WAB is equal to the 2-player winning probability, and probability of WAB and GE is the 3-player winning probability. We have that the probability of Eve not guessing condition on Alice and Bob's winning event is upper bounded by this quantity, using literally the definition of condition probability from high school. You can rearrange. You basically solve for this probability of GE. You can show that it's upper bounded by 1 minus the 2-player winning probability plus the 3-player winning probability, which means the min entropy, which again is the negative log of the guessing probability. This is probability, which is this quantity. And there you go. That's your bound to the entropy of every round that we care about. And to put some intuition on what this means, I've got some nice graphs. So for any, and this works for any game that satisfies monogamy of entanglement, for any game that the 2-party winning probability omega-2 is larger than the 3-player winning probability of omega-3. You can put these values on like the Devetak-Winter rate, and you find the range of values of omega-2 and omega-3 that give you a positive key rate, as given by the asymptotic rate from before. And in particularly for the magic square game, in the finite number of round case, and for different errors in your source, you can calculate the amount of key rates that you, Alice and Bob, generate. And yeah, that concludes the chronology of QKD talk. Thanks for paying attention.